Oh, there we go.
Okay. All right. I think it's working now. Everybody, sorry, thank you for patience. Not sure what the hang up was. All right, so we'll jump right into it. Jay's gonna give us our last talk of this quarter. Jay did his undergraduate and PhD at Stony Brook with Bill Holt. He did most of his research focusing in California, faulting and so forth. And that's what he's going to talk about today is what he's doing. He did this as for his PhD research. Jay's postdoc now working on the COPES project, COPES Hub project. So hopefully several months he'll be back to share his more recent work. So anyways, Jay, take it away.
All right, thank you very much, everyone, for coming, and thanks for introducing me. Today, basically, I'm going to present my PhD dissertation, so I consider it my second defense. So hopefully I can get many feedbacks for my future research, and it would be great if I can discuss science with you. So before I start my presentation, let's think about do you think I should get rid of that? Okay. Let's think about continental deformation first. And let's say we are first year undergraduate student, and let's think about plate tectonics first. This plate tectonic theory is great because it provides a framework that describes the kinematics of the plates on the surface as the rigid body rotation. Yeah. And this theory has two major assumptions. And the first assumption is that all the plates are rigid, therefore there is no internal deformation. And all the strain is concentrated on a narrow boundaries between plates. And today I'm going to focus on this plate boundary zone here, which is continental plate boundary zone, separated by roughly saying San Andreas Fault, and we have two plates, North American plate and Pacific plate. And Pacific plate is moving faster than North American plate, so therefore we would expect a lot of shearing along the San Andreas Fault. But you already probably know the answer, but if you think about these two major assumptions, then you may not believe these, because if these two assumptions are true, then if I plot seismicity, then all the seismicity should focus along the San Andreas Fault. So I plot seismicity from USGS over the last decades, and here is the result. They are everywhere. Therefore, these two assumptions are not suitable for continental plate boundary zone. And one of the important characteristics of continental plate boundary zone is diffuse, and therefore the horizontal dimension of those plate boundary zones are very large. It can be hundreds to thousands of kilometers. Then my next question is that then how to quantify deformations for continental plate boundary zones? Because it involves a lot of faults, very complicated fault. I plot major fault system here from USGS as well. Here, I didn't plot minor faults, blind faults that have no surface traces, and we all know that there are many unknown faults here, but it's already very complicated. One way to quantify deformation for complex system is to obtain continuous displacements over space. Then you can take spatial derivatives, and that will tell you the spatial variations in deformation. Let's think about a very simple example here. You have elastic material, and you have displacements. And from these displacements, if you take spatial derivatives, then you can tell it's extensional. You have another set of displacements, but the spatial derivatives are the same, therefore you have same extension. Now you're squeezing this material, therefore it's contraction, and you have different set of displacements, you're fixing one side, then you're squeezing the other side against the fixed side. It's another contraction. So all I want to say is that if you know continuous displacements, then you can tell the status of strain or deformation. And if you can have time-dependent continuous displacement, then you can also quantify time-dependent deformation patterns. So these are background before I go further. I wanted to share. My dissertation is made of 5 chapters and it has 3 main chapters. In chapter 2, I studied large-scale deformation over space and time within this large region here shown in the map. And I also investigated dynamic source of the time-dependent deformation. In chapter 3, I characterized 13-year detailed history of deformation patterns in Ridgecrest area. This area is interesting because there were 2019 Ridgecrest earthquake, magnitude 7.1. It was the largest inland earthquake in California over the last 20 years. And then I investigated a possible implications of time-dependent deformation on seismic activities for this region. And I performed a lot of statistical analysis. And in chapter 4, I developed a new joint inversion algorithm of INSAR and GNSS for better deformation model. I wanted to increase the spatial resolution of my model. Since it's a new tool, I performed a lot of sensitivity testing using synthetic data sets. And then finally, I applied this technique to a real data set. This is the title of chapter 2, cross strain patterns associated with normal drought and heavy precipitation years in California. This is a published work in JGR, Solid Earth. I have 2 co-authors, Dr. Ali Badri, he's a postdoc at Lamont, and Bill Holt, my PhD advisor. And this work is also highlighted in EOS. So if you're interested in and want to read a plain language.
Cool.
Things, then maybe you can read this article. In California, we have about 900 GPS data. In this talk, GNSS is a comprehensive term that includes GPS, but in this talk, I'm just using GPS and GNSS interchangeably. So please don't get confused. This is GPS receiver. What you do is to install GPS receiver into the crust. So as the crust moves, your receiver moves together. So you are tracking those motions of receivers, then that you are actually tracking the motions of crust for its location here. Using this technique, we obtain these displacements, 900 displacements, and you can see the scale here. And our group, my previous group, has a tool to interpolate these finite number of GPS displacements to obtain continuous displacement. Here is steady state continuous displacements. And fortunately, after the onset of EarthScope PBO project, we have a lot of continuously operating GPS site, means that we have GPS time series, position time series. Therefore, we can obtain continuous displacement as a function of space and also time. So I plot steady state field and non-steady state field from GPS time series. And as you can see, they are moving slightly over time. You can track the time here, it's monthly solution, and the scale is 1 millimeter. And I took steady state field and subtracted out from non-steady state field and plot residual field to see what it looks like. I rescaled to show you the residual field better. And you can see this. And they are oscillating seasonally, moving back and forth. And I want you to focus on this area around latitude 37 north. During the winter, your crust moving toward the center, but during the summer, they are moving away. Let me play one more time. During the summer, they are moving away, and winter, they are moving in. Summer, they are moving away, and it repeats over the last 13 years. And again, I have continuous residual displacement as a function of time, therefore I can obtain deformation as a function of time. The background is horizontal gravitational strain. Red means extension, blue means contraction. Here during the winter, around the Great Valley, you have a lot of contraction because your displacements are moving toward the Great Valley. But during the summer, the strain pattern is opposite because they are moving away. And it repeats. And after I see this kinematic model, I wondered what's the dynamics, what drives these seasonal variations shown in horizontal deformation.
To the -8.
So I focused on the patterns of precipitation in California. I plot precipitation amount along the y-axis as a function of month. And from this plot, you can tell California has wet winter and dry summer. So maybe this seasonal horizontal deformation can be explained by those seasonal variations in precipitation in California. There were a bunch of previous studies that discussed about the vertical seasonal movements because of the seasonal hydrologic loading on the surface. But right now, in my talk, I'd like to focus on the horizontal flow. So when you add a lot of water on the surface during the wet season, which is winter, your elastic crust should subsidize. At the same time, horizontally, it's moving toward the center of the load. But during the drier season, which is summer, you're losing a lot of surface water because of the precipitation pattern, then your crust is rebounding back and horizontally it's moving away. So that's the qualitative description, but we wanna quantify this. And this is horizontal elastic Green's function response to surface disk load. So y-axis is horizontal displacement and x-axis is the distance between a disk load and a station. To obtain this Green's function, I use JPL software, ISSM, and it involves a lot of math. It's very difficult to obtain, but once you obtain, it's great because you can use this function as a kernel function and the system is linear. So all you need to do is to have water thickness and multiply the thickness by this Green's function response, then it will give you the horizontal response. And here I have this load and as for an example. Let's think about zero thickness first. You have no water, so water thickness is 0. So if you multiply 0 by any function, then the result should be 0, right? So you have no response at the station. But when you add a little bit water, then you start to have horizontal response. And when you add more water, it's scaling up. Keep going.
Water's over there. GPS is there.
And it can be varying based on the thickness of the water. That's all I want to say. And as I told you, that it's a linear system. So if you have more than one water loading disks, then you just have individual responses and take summation. That's gonna be the final horizontal response. You have 3 loading sources and you just add them all. And now you have continuous surface water across the region, then you just take integral as a with respect to an area. And if your loading estimates are time dependent, then you can quantify horizontal time dependent responses as well. So only plot one station here and then I'll play this movie. And as the distribution of water varies over time, the response at the station also varies. And we can calculate these responses everywhere within this area. So I quantify horizontal responses at each of those 900 GPS sites, and then I obtain these time-dependent elastic responses. You can track time here, and they are moving back and forth. When you add water, they are moving in. When you lose water, they are moving away. Not,
Color showing us precipitation amount
oh,
per unit of time.
yeah, sorry about that. It's a water equivalentiness in meter. So the bluer color you see, the thicker your water is. Or I forgot to explain that color. Yes.
The water moves though in this, probably there a permeability of the rocks and so on. What is that
Yeah.
factor into the?
That's a good question. The water estimates here are soil moisture, only taking account 2 meter soil layer plus surface snow. And in this study, I didn't consider any permeability and time lag, something like that, or photoelastic responses. And to justify that, before I use GPS data, I analyze vertical time series. And if you see the vertical response, then you can roughly say that station is affected by photoelastic or elastic. If it's affected by elastic, when you add water, you should expect substance. When you lose water, you should expect uplift, right? But for photoelastic, when you add water and it fills up the porosities, therefore you have uplift. And when you lose water, you have space, therefore maybe collection happening, therefore subsidence. So the vertical response are totally different. That's how I can distinguish stations affected by elastic or photoelastic. And in this case, I only considering elastic responses. Yeah, now I have time-dependent GPS independent displacements, and I treat them as if they are GPS, and then I apply the same interpolation algorithm to obtain continuous field. And this is kinematic model for winter that I showed, which is inferred from GPS horizontal data. And these two are my dynamic models. They are horizontal GPS data free. They don't know about horizontal data at all. And if you focus on the spatial pattern here for winter, they look very similar. And for the summer, I also compared, and they also look similar. Now I just look similar, but I did quantitative comparison in my paper, so I can say quantitatively they are similar. Here for the talk, I just like to say they are similar. So we concluded that such seasonal deformation, horizontal deformation pattern in California can be explained by the Earth's elastic response to the surface loads because of the precipitation patterns in California. If my statements are true, then our model should show you something other than seasonal, such as multi-annual variation, because California has undergone severe drought many years, and also it has extreme weather events such as heavy precipitations. And this year they are experiencing heavy precipitation. There are two satellite pictures from NASA, and they both taken during the winter, and that on the left, that was taken during the drought winter, and this on the right, that's taken during the heavy precipitation year of 2017. And you can tell that the amount of snow on the surface are quite different, although they are both taken during the winter. So I wonder if my model can explain such multi-annual variations. So I plot these three panels together. And on the left, that's winter signal during the drought, 2014. Because of drought, you add less water during the winter. Therefore, your horizontal response is smaller compared to normal winter in the middle. But during the heavy precipitation year of 2017 here, or 2019 and 2011, you add a lot of surface loads on the during the winter. Therefore, your horizontal response is a lot larger compared to normal year. And it's the same for the summer, because you add less water during the previous drought winter. Therefore, the following summer, you should have less rebound signal, but compared to normal summer in the middle. But during the heavy precipitation summer, which is about 6 months after the heavy precipitation on the surface, you lose a lot of water. Therefore, the rebound signal is higher. Therefore, we have higher extensional signal here. And
What's the average difference between the GPS displacement during a drought winter and normal winter? Is it like on several millimeter scale or sub-millimeter scale?
it's about during the drought, the signal in dilatational strain is about half the normal dilatation. Yeah. So the volume change is twice smaller compared to normal. And it can be 200% larger during the heavy precipitation year. So I showed you the kinematic model inferred from GNSS data shows drought, normal, and heavy precipitation signals. And now I'm wondering about the dynamic models. They also show such multi-annual variations. And my answer is yes. So this is kinematic model and two dynamic models that I showed for the normal winter. And this is for the heavy precipitation winter signal. And they both, all the three models shares multi-annual variations during the heavy precipitation year, winter in 2017. And it's also same for the drought year. So it's the conclusion of this chapter. Horizontal residual displacements as a function of time and space and associated crustal deformation patterns can be attributable to Earth's elastic responses to large-scale surface hydrologic loads pertaining to precipitation patterns in California. And in next chapter, the title is Repeating Non-Tectonic Seasonal Stress Changes and a Possible Triggering Mechanism of the 2019 Ridgecrest Earthquake Sequence in California. It's another paper published in JGR Solid Earth. I have same co-authors and one additional co-author, Professor Wei-Sun Shen. He visited us last January, and he provided very important idea. So he's on a co-author, and he was my PhD defense chair. So, but previously I quantified deformation pattern over space and time, and now I'm wondering, is there any possible impact of time-dependent deformation on seismic activities? That was my question. And I had two major hypotheses. The first hypothesis is that seasonal crustal strain stress changes result in seismicity rate changes within the plate boundary zone. And the second hypothesis, which I think it was quite ambitious, is that large earthquakes also can be triggered by seasonal stress changes. Here, what I mean by large earthquake is if an event larger than, I don't know, 5.5, then I consider it large, because I'm only considering crustal earthquakes, not megathrust type earthquakes. And to test these hypotheses, I focused on Ridgecrest region for some reasons. Here, I boxed Ridgecrest area, and I plot earthquakes larger than magnitude 2 over time. And as you can see, this area is seismically very active. And in 2019, July, there were two large earthquakes, magnitude 6.4 full shock, followed by magnitude 7.1 main shock. There were two large events, so this area was perfect reason to test the second hypothesis. And lastly, this area is covered by dense, continuously operating GPS data. Therefore, we can also quantify deformation pattern for this. Fine, yeah.
So, question about the premise of the second hypothesis. Usually the notion of a trigger is just something that initiates a failure.
Yes,
Oh, over.
So how big the earthquake gets is, unless you believe it's predetermined, is dependent on something other than the trigger.
right.
So why hypothesize that it triggers any earthquake of any particular size? Is that an observational thing or?
That's a good question. We only found two large events in California are coincidentally occurred during the seasonal stress in peak, but we only have two sample sizes, so we don't know. But what we assume here is that it, as you said, it's a triggering that the crust is almost close to the failure, and if you add a little bit, then it may fail. That's the big assumption. And we didn't actually systematically hypothesize that sentence as considering the magnitude dependent earthquakes.
So in a sense, it's preconditioned to be a big earthquake.
Yeah. So I picture that it's about to fail, and you just need a little bit help. That's what we just assume. It's big assumption, and we didn't even consider dynamic triggering that you showed. It's just very simple. We didn't mention, but implicitly we are assuming Coulomb failure criteria as well. Okay, so previously I showed displacement field can be obtained using GPS data, and then you can obtain deformation patterns because the spatial derivatives of continuous displacement is strain. And if you know fault geometries roughly and elastic moduli and friction on the fault, then you can convert to your strain as a function of time into the stress changes as a function of time. Here I plot Coulomb stress changes resolved on vertical right lateral strike slip fault. The red is positive Coulomb stress change, means that your fault is easier to fail compared to Coulomb stress change of 0. And blue means negative Coulomb stress change. That means your fault is harder to slip compared to 0 Coulomb stress change. And I'm going to play this movie here. It starts from January and it's a annual solution, so it will end in December. I wanted to focus on this area surrounding these two epicenters here. During the winter, January or December, you have negative Coulomb stress change. But as time goes, it increases and it's in peak in May and June. And then it decreases again. And during the winter, it's in negative Coulomb stress change. It repeated over the last 13 years from 2007 to 2019. And we found this solution is quite interesting. And these are two snapshots for winter and for June. I plot Coulomb stress time series here. And when I plot this, I use steady state tectonic loading rate as well. So it's just superimposed on the steady state tectonic loading rate, which is the linear line. And I indicate every June using these arrows. And as you can see, every June you have stress peak. It's quite interesting, all the way to this point, which is June 2019, just the month prior to the 2019 Ridgecrest Earth. As I said, it's just one observation. It can be totally coincidence. But if I move further, I want to point out that the amplitude of seasonal stress change is only 0.7 kilopascal. It's very small. You may think it's too small, but as I told you that I considering it as a triggering factor. 0.7 kilopascal, but the geodetically derived geodetically inferred tectonic loading rate here is 1.4 kilopascal per year. So if you're considering the ratio of these two values, then it's 6 months. That means that the timing of earthquake can be advanced or delayed by up to 6 months because of seasonal stress changes.
How large is that 0.7 kPa compared to tidal stresses?
Tidal stresses can be larger. Yeah. I cannot say how large, but tidal is larger. And some people discuss about seismic the nucleation of seismic failure, and maybe tidal is too short for seismic activities. And yeah, I don't know. I don't know what's true.
So, do you look at any earthquakes with smaller magnitudes, like ones that are like in the 3 to 5 range? I feel like if you're seeing too long stress changes, you see more earthquakes of all magnitudes, not just very big ones.
Yeah, that's exactly the comment that I got during the AGU 2019, and I am about to showing that with you. Thank you for the comment. So yeah, it's one sample. So I try to include all the earthquakes larger than 2.0 actually, not 3. For that, I actually needed to use declustered catalog instead of full catalog because you need to make sure all the events are independent. Otherwise, your statistical analysis doesn't make any sense, right?
Don't you also need to know the geometry and the structure plane?
Yeah, that's another true. Here, we obtained low length change directions using GPS data, and then we compared that with focal mechanisms, and within 2 degrees they are agreed. So we believe we using pretty reasonable geometry. Or you can, since we have dynamic model, then we can take fault planes from focal mechanism, and we can just quantify stress on the fault planes. That's another way to go. But here I comparing my kinematic model with the earthquake events. But there are some studies about that. Yeah. So I did 2 different things. From the clustered catalog, I already know the exact timing of earthquakes. So I counted how many more earthquakes actually occurred during the stressing period, here shown in the thicker red line. Stressing period is the all time period that has new stress high. So you pick one time and compare with previous stress values, and that value is higher than any previous value. That's new high, and we define that period as stressing period. And we count how many earthquakes actually occurred during the stressing period compared to other period, which is relaxing period. And here our model has error uncertainty, so we repeated this counting over and over again 100,000 times, and each realization we added random error based on our model formal error. So first of all, again, I count how many more earthquakes actually occurred during the stress period using correct timing of earthquakes. And I obtained this distribution, orange color distribution, and it tells you have 25% plus minus 10% more earthquakes actually occurred during the stressing period. And next, I just ignore the timing and I just temporarily randomly distributed earthquakes, and I repeat the same procedure and then count how many earthquakes occurred during the stressing period. Then I got 0% plus minus 20% more earthquakes during the stressing period from this random test. Here, excessive number of earthquakes in 0%, that means earthquakes occur regardless of seasonal stress changes. And if you compare this 0% with the orange distribution, then the p-value is about 0.01, which means with 99% confidence, then you can reject this new hypothesis that earthquake occur regardless of seasonal stress changes. It was great, but we believe this second comparison is better. We just try to understand what's the overlap between these two observations to test this observation and random tests. And the overlap is about 39%. And that actually tells you that our observation, 39% of our observation can be derived by a random process, which is unfortunate. But if you compare the average value, assuming that our model doesn't have any uncertainty, and compare this line with the blue distribution, then the p-value is about 5%. So we can still reject that earthquakes occurs randomly, that null hypothesis with 95% confidence. But again, it's uncertainties. Taking into account the uncertainties are very important. So we only have about 65% confidence to say that our observation is not from a random processes. And this is conclusion slide for this chapter. Seasonal stress changes may have modulated the timing of the 2019 Ridgecrest earthquake by 6 months. And our statistical tests support this possible triggering mechanism, showing a correlation between the timing of small earthquakes and the seasonal stress changes with 2 sigma interval. But if you take into account the model uncertainty, then the significance level becomes slightly less than 1 sigma. But if you think about the uncertainties in Earth data, we still believe 1 sigma is something meaningful, especially for geophysics. So we finally concluded that there is strong need to continue the monitoring seasonal deformation patterns because it may do something on seismic activities, and future studies are needed. And it's important to improve our deformation model. That motivated my last chapter here. So we developed a joint inversion of INSAR and GNSS to improve our deformation model. This work is in preparation to submit. And if you think about the average spacing between any 2 GPS stations in California, it's about 5 to 10 kilometers, meaning that you have huge data gap between 2 stations. You don't know actually what's happening with relying on interpolation technique. So you may have something happening in the middle between any 2 stations. And because of that, the highest spatial resolution of our deformation model is about 50 kilometers. If you go smaller, if you try to obtain higher resolution than 50 kilometers, then your model starts to have a spatial aliasing problem, making many weird artifacts. You don't want that. So we wanted to add INSAR to fill the data gap. Because of time, I just want to skip here, assuming that you know INSAR. Basically, it measures two. It has based on two SAR images. You can build an interferogram, and from that you can have phase differences over time. You already know the wavelength of microwave for SAR, and you know the time interval between two measurements, so that you can convert that phase difference for velocities or displacement across the entire swath. But INSAR has one problem, which is it doesn't measure all the three components for displacements. It only gives you the 1D projected displacement or velocity along the line of sight direction from satellite to the target pixel. On the other hand, GNSS measure all three components of displacement, which is great, but again, it has spatial issue. INSAR, it only measure 1D, but it can provide continuous imaging of displacements. So they are highly complementary to one another. So we wanted to combine these two to obtain 3D continuous velocity field to improve the quality of our deformation model. And for that, we focus on Southern California. And this is method section. It's another linear system that we obtained about 1,400 linearly independent basis functions. We obtained these basis functions by solving force balance equations using 4 different body force equivalents, assuming the basal traction is 0. It's some technical stuff, and we try to obtain the best model that the linear combination can predict both INSAR and GNSS at the same time. That's the key, and for that we had to obtain this G inverse. It's non-unique problem. It's quite difficult to find what's the optimal solution, but we had some tools. Specifically, I use tenfold cross-validation to get an optimal solution. If you are interested in this stuff, then maybe we can talk later, but for time, I'll just go and show you the result. That's INSAR data number 1. It's a descending track INSAR. INSAR data number 2, it's ascending track INSAR measurement, and that's GNSS. That's prediction INSAR data number 1. That's prediction INSAR data number 2, and that's prediction of horizontal GNSS together with continuous field. So we now have continuous field. Here I plot the second invariant of strain rates as the background. And you can, when you see a darker color, that means the cross is deforming faster. That's, you can just consider the second invariant in that way. And the crosses, the red bar, indicates the maximum extensional direction, and the gray bar indicates maximum shortening direction. These are principal axes of strain rates. And you have two major faults here, San Andreas fault and San Jacinto fault, and that's the joint inversion result. And that's GNSS alone solution that I used in the previous chapters. Again, that's joint inversion, that's GPS alone. So I think joint inversion is slightly better than INSAR alone solution in terms of the spatial resolution. And we can also obtain vertical displacements from that. There are some suspicious signals here, but the result is similar to the other group's vertical displacement. So we believe the joint inversion works for the vertical, but maybe there is some issue in the INSAR data set. But it can be used for tilt or vertical displacement as well. So the conclusion is that the algorithm works, which is good. And in the future, I'd like to add more constraints in addition to INSAR and GNSS, because my goal is not just developing a joint inversion of INSAR and GNSS. My goal is to improve deformation patterns for better research or effect on seismic activities. And I can apply this for the entire plate boundary zone in addition to the smaller area in the future. And I can also use it for the time-dependent model. And I believe this approach has broad implication. It can be used for volcanic activity monitoring and permafrost monitoring and tracking any fluid subtraction near surface and also tectonic studies. And to refine these types of algorithms are very important right now because the amount of INSAR and GNSS data will expand exponentially in the future together with future SAR missions and the fact that GPS receivers price getting decreased. So people installing GNSS stations everywhere around the globe. It's just final conclusions and I'll skip and I leave my thank you page here. I have a lot of people to thank and then I'll finish my talk here. Thank you.
Okay, so it's just about 1 o'clock. If we have to run off to a meeting, please feel free to. Otherwise, we'll allow some time for questions.
The length of screen, the biller about 1 million, but it's pretty big.
Pretty big.
I thought so. So for example, if you were to do your work up here in the west and east and Washington, the low screen rates, they're all very slow.
Yeah.
I would imagine that there possibly the signal would kind of overwhelm. Misjudge that. So, and